So the fundamental theorem of finite abelian groups gives us the tools that we're going to need to classify all possible abelian groups of a specific order. So let's, for our exercise to get started today, think about abelian groups whose order is 350. Two things I'd like to be able to do. First of all, make a complete list of all abelian groups of order 350. And then second thing is to be able to review that list and decide which of those groups contain an element of a specific order, of order 25 in particular. So one of the theorems that we haven't proven yet, which is the crown jewel of chapter 7, it turns out, is that the order in any group of an element in a finite group must divide the order of the group. And 25 is indeed a divisor of 350. So it's possible for a group of order 350 to have an element of order 25. But by doing this classification process, we should be able to figure out which of your examples do and which ones do not. And of course, the orders of elements are a powerful way to distinguish between groups that are not isomorphic. So there's your prime factorization of 350. So with the rules of the StackIt game that we played on Wednesday in mind, what should we be thinking about as far as what's going to create for me some different abelian groups? So remember, one option that I always have is just to stack all these chips into one stack. Now, what abelian group would I be talking about there? Yes, that would be the group Z350. Yep. So that's what I get if I just stack all of these on top of one another. On the other hand, at the other end of the spectrum, what could we do? What if we did no stacking? Now what do we have?
Z2 plus Z5 plus Z5 plus Z7.
Exactly. We have all of them in their own separate factors, Z2, Z5, Z5, Z7. And how do I know whether or not that is distinct or is it isomorphic to Z350? So we can find new presentations of the same finite abelian group just by using the rules of the game, right? The rules of the game are that we cannot separate a family of the same color from a given stack, so I couldn't separate these two blues from one another. And we cannot add a color to a stack if that color is already there to begin with, right? But this move satisfies both of those criteria. I can move this one blue chip on top of this one red chip, and this now is a legal position in the same StackIt game as this, right? And it corresponds to the direct product Z10 plus Z5 plus Z7. So that is isomorphic, therefore, to Z2, Z5, Z5, Z7. Okay, so let me ask this question. Of the three groups that we see here on the screen right now, which of these groups do we think has an element of order 10 in it? What might we represent by a 10 in this game? I think it's pretty easy to convince yourself that the example we just wrote down has an element of order 10 in it. Where might that element of order 10 come from? So I'm going to give you a little sneak preview into what we're going to talk about when we talk about direct products. But the fact that this is a direct product means that its elements are ordered, in this case, ordered triples. X, Y, Z. Where the X's are taken from Z10, the Y's are taken from Z5, the Z's are taken from Z7, and all the arithmetic that happens with the arithmetic of those groups. So the first components are going to add using addition mod 10. The second components are going to add using addition mod 5. The third components are going to add using addition mod 7. So where am I going to find an element of order 10, do you think? I'm going to find it in Z10. What's an example of an element of Z10 that has order 10? 1. Sure, the generator. An example of a generator would be 1. So inside of this group, if I make my first component 1, that first component is going to come back around to the identity after I add it to itself 10 times. But how do I make sure that these other two components don't screw that up? Okay, if I had also put a 1, let's say here, then that's going to come back around to the identity after how many additions? 7. And so at the 10th addition, this one's going to be 0. But this is going to have come back around to 3. Right? And so my whole element is not going to be the identity element of the product. To be the identity element of the product, all 3 of those entries have got to be zeros. It's almost like a car odometer, except the odometer numbers have different numbers of teeth on the wheels. Right? I want to make sure that they all come back around to 0 at the same time. So if I want this to for sure come back around to 0 after 10 iterations, what could I, for example, put in the second and third entries? Yeah, put zeros there, right? That way, when I add those to themselves, nothing's going to change, and this 1 is going to come back around to 0 exactly at the 10th time. Right? And so there is an example of an element of order 10. In my picture, what is 10? 10 is 2 times 5. Right? And so 10 is nothing more than a stack that has a red chip and a blue chip both in it. Right? So here is an element of order 10 right there in that group. Is there an element of order 10 in Z350? Just looking at the picture.
Because 10 divides 350.
And because Z350 is a cyclic group, it will have an element of any order that divides its order of the group. Right? Any divisor of 350, we can find an element of order 10. Or sorry, an element of that order in the group. And since 10 divides 350, we have an element of order 10. And what's great about StackIt is that that means that I can find a configuration for Z350 in which I can find the number 10 inside of the same stack. Right? A red and a blue sharing the same stack. That shows me that 10 is a divisor of the order of that cyclic factor. And therefore, an element of order 10 exists in that cyclic factor. And if we just put zeros in the other factors, we can ensure that that element therefore exists in the whole direct product. So both of these groups on the screen so far have elements of order 10. What about elements of order 25? How does the game change? What would an element of order 25 look like in this game? So 25 here, represented by a stack of 2 blue chips together, 5 times 5, right? And Z350 has it. Because 25 is a divisor of the order of the cyclic factor, Z350, there exists an element of order 25 in Z350. But how do I know for sure that no isomorphic version of this group will have an element of order 25? What do we have to get in order to get an element of order 25? We have to be able to stack the 2 blue chips together, which we cannot do without ruining the isomorphism class. Right? And so that reconfirms for us that these 2 groups are not isomorphic because Z350 has an element of order 25, but the other one does not. Right? So yeah, the more that I've been thinking about this game that we started playing earlier this week, the more I'm realizing we can get a lot of mileage out of it. A lot more mileage than I thought. Right? We can figure out now, given any stack, any arrangement of chips, whether or not we have an element of a certain order. We just have to look for that order as part of the same stack. Right? Then we know for sure that if it can't be restacked to have that combination of primes in one of the cyclic factors, then it doesn't have an element of the order, and it's if and only if. Right? If we can stack it in that way, then because a cyclic group is going to have elements of every order that divides the order of the group, if I can find that divisor as part of the same stack, there is an element of that order in that stack. So the other configuration that we can write down here is Z2, direct product with Z35, direct product with Z5. Okay. And that one is isomorphic to these other 2 down here. So how many total, I'll get to your question in a second, how many total distinct isomorphism classes of abelian groups of order 350 are there? There's only 2. There's the one up here on top, and there's the one over here on the bottom. And we could have also used StackIt moves, right, to find different ways of understanding Z350 by unstacking some of these chips in legal ways, right? For example, we could have unstacked the 2 blue chips and then maybe left the red and the green. What presentation of direct product of cyclic groups do we get there? 25 and 14. And so that direct product is isomorphic to Z350. Give me one more.
Two blues and then the red by itself and the green.
Red by itself, green by itself. Yes. And there's a presentation with 3 cyclic factors, 25 and 2 and 7. All of those are isomorphic one to another. Right. And how do we know that there aren't more non-isomorphic examples? What was the way that we had to count how many distinct games of StackIt we can play with a set of materials? Casey?
You use the partition function.
Partition function. I would multiply the partition function of number of red chips, 1, multiplied by the partition function of the number of green chips, 1, multiplied by the partition function of the number of blue chips. What's partition function of 2? It's equal to 2. So 1 times 2 times 1. There's only 2 isomorphism classes. Only 2 distinct games we can play of StackIt with this material. One more isomorphism example from the bottom row. Why not stack the red and the green together? Right? That's a legal move. As long as we're keeping the blue chips separate, we're not going to end up in a new isomorphism class. Right? So yeah, let's get that one down too. Good catch. So red and green, but the blues are separate. What direct product does that give us? Z14, Z5, Z5. Yeah, good. Now I think that actually does it. Now I think we're done. Good. So yeah, I mean, we found another, thank you, found another example of a way to present this same group. So one of the things this should cause you to do, just thinking as an abstract algebraist for a minute, is not necessarily to believe your lying eyes, right? If somebody gives you this group and somebody else gives you that group, they look on their surface to be quite different, when in fact they're isomorphic. They're actually different presentations of the same finite abelian group. And just to wrap things around and tie a bow around this, why is it? What's the mathematical name that we give to stacking these 2 chips? Like, how do I know that I can stack this green chip with this blue chip? What is it about Z5 and Z7 that tells me that their direct product is indeed isomorphic to Z35? Casey?
5 and 7 are prime.
5 and 7 are prime, which there's actually a weaker condition that they need to satisfy. Relatively prime. Yes, they're prime, and so in particular, they're relatively prime. Yes, very good. So as long as P and Q are relatively prime, we can stack those together. So 25 and 14, neither of those are prime, but they're relatively prime to one another, and therefore I can combine both of their stacks together to make one stack, Z350.